Welcome to the deep dive. Today we're getting into something really foundational for how physical things get made. Orthographic drawings in manufacturing.
Yeah, absolutely. Think of them as the secret language almost. The blueprints that turn complex 3D ideas into, actual objects. It's essential everywhere. Factories, design offices.
It really is. So our mission here is to dive into the source material and figure out why these specific 2D views are so critical. What makes them, well, indispensable.
It really comes down to communication. Taking something complex, maybe a 3D shape, and explaining it with absolute clarity. No room for error. That's the goal. Precision.
Okay, let's unpack that. Why these specific drawings? Why not just say a really good 3D model picture?
Well, a picture, like a perspective sketch, it has distortion, doesn't it? You can't easily measure from it accurately. Orthographic drawings give you these flat 2D views, straight on front, top, side.
Ah, like looking at it from fixed points.
Yeah. Exactly. No distortion. So you can pull precise measurements right off the drawing. And that level of accuracy is, well, it's non-negotiable for making lots of something or making sure parts fit together. Interchangeable parts.
Right. Okay. Avoids the guesswork, ensures things actually connect. And this works globally.
That's a huge part of it. Yeah. Standardization. Following rules like ISO or ASME in North America, it creates this universal visual language.
So a drawing made in Germany can be used in Japan, no problem.
Precisely. Regardless of spoken language. It cuts down on misunderstandings, which saves time and, frankly, a lot of money. It's the grammar of making things, really.
A universal grammar based on lines and numbers. Fascinating. Yeah. And these drawings, they contain everything needed.
Pretty much, yeah. They're more than just pictures. They're full instructions.
Yeah.
You get the shape, sure, but also dimensions, geometric tolerances. It's about how much variation is allowed so parts still fit.
Okay.
Material type, surface finish, like how smooth it needs to be. All the info from raw material to the finished, inspected product.
Wow. And you mentioned they can even show things hidden from view. How does that work?
Absolutely. That's where the different line types come in. It's like a code. For features inside the object, maybe a hole or a cavity you can't see from the outside.
Yeah.
We use hidden detail lines. They look different. They're usually thin and dashed. They show you what's behind the surface you're looking at. Crucial for avoiding mistakes about internal stuff.
Ah, so every line has a specific job. It's not just random dashes.
Not at all. You have your main outlines, thick, solid lines showing the edges you can see. Then, like we said, those thin, dashed, hidden lines for the internal features.
Okay, got it. And I heard there are lines that aren't even part of the object.
Right, projection lines, or sometimes called construction lines. They're super thin, often drawn lightly.
And their purpose?
They're guides. They help you line up features between the different views. So a hole, shown in the top view, lines up perfectly with its position in the front view using vertical projection lines.
I see.
Or there's a neat trick with a 45-degree line, a miter line, to transfer depth information between the top and side views. They maintain that strict spatial relationship. They keep everything aligned.
Speaking of alignment, the source talks about third angle projection. What's that about?
It's a standard way of arranging those views on the paper. Very common in North America. The idea is pretty intuitive, actually.
Okay.
Imagine the object is floating between you and the page. So when you look at the top, you draw that view above the front view.
Makes sense. Top view goes on top.
Exactly. And when you look at the right side, you draw that to the right of the front view. It follows where you see it from. What you see is where it's drawn, basically. Simple, right?
Yeah, that seems logical. And there's a symbol for this.
Yes, the third angle projection symbol. Critically important.
Yeah.
It usually looks like a small circle inside a bigger circle, representing the front view of a cutoff cone.
Right.
And next to it, a sort of trapezoid shape, which is the side view of that cone.
Right.
Its only job is to tell you, unambiguously, this drawing uses third angle.
Why is unambiguous the key word there?
Because there's another system, first angle projection, common in Europe and elsewhere, which arranges the views differently. The top view goes below the front view, for instance.
Oh, I see. Mixing those up would be bad.
Very bad.
Yeah.
You'd completely misunderstand the object's shape. Imagine machining something based on the wrong interpretation. Huge, costly errors. That little symbol prevents all that. It's the key to reading the layout correctly.
Okay, so we have the views, the line language, the projection method arranging them, the symbol for clarity. But none of this tells you how big to make the part, right?
Dimensions. You absolutely need dimensions. A drawing without dimensions is, well, it's just a shape. It's not manufacturable.
So dimensions are the numbers.
The numbers, the symbols, like that circle with a slash for diameter phi, 10 millimeters means a 10 millimeter diameter hole. They define size, location, distances, angles, everything quantitative.
And they do more than just define size.
Oh, much more. They define the exact size and shape, yes, but also locate features precisely. They ensure parts are interchangeable, especially with tolerances. They guide the actual making, where to cut, grill, bend,
Guiding the process.
and they're essential for checking the final part. Quality control. Inspection. Verifying it matches the design.
So they really turn the drawing from a picture into instructions.
Exactly. They eliminate all the guesswork about size and position. They give the data for machines, make sure things fit, prevent waste, and they even act as a sort of legal contract for what needs to be delivered. Dimensions make it actionable.
So putting it all together, these orthographic drawings with their specific views, the code and lines, standard projection, that crucial symbol, and the dimensions, they form this incredibly precise universal language for manufacturing.
That's it, exactly. It's a whole system designed over years to get rid of ambiguity, maximize accuracy, and let people collaborate effectively wherever they are.
And what really strikes me is thinking about this system, all these lines and numbers, sort of the invisible code behind almost everything manufactured around us. Just, look around you right now. How many things in the room were made possible piece by precise piece because of drawings like these?